And we did all this stuff yesterday. Let's start today here. We need our calculator. So yesterday we worked one problem where we made a table and we looked at what's happening numerically when we substitute values in as we approach our C value. Today, that's where our big focus is. Okay, so let's start out, and hopefully this thing won't freeze on me again today. I like the blue color. Let's start out. Let's make our table. Let's get our numbers ready that we're going to put into our calculator. So we get everything ready to go before we start doing it. Okay, I'm going to put 0 in the middle. Now we're going to approach 0 from the left. So over here, it's going to be the limit as x approaches 0 from the left of, obviously, the function x over square root x plus 1 minus 1. Okay? So over here, we got to pick numbers to the left of 0. What should be, let's go, negative 0.1. Oop. We'll pretend that didn't happen. And then negative 0.01. And then negative 0.001. And then over on this side, we'll be looking at what's happening as we approach 0 from the right. And again, it's going to be of x square root x plus 1 minus 1. 0.001 on the positive side, 0.01, and then 0.1. Now we use your calculator. Hopefully this does not freeze my computer this time. Let's see what happens. Clear out anything you have from yesterday. We got only one term in the numerator, so I can just put x. I don't need parentheses around the numerator, but if you feel more secure doing it, go ahead. Divided by, begin parentheses. Square root, that's above the square key. It's a blue function, so blue key. X plus 1. Arrow out of that, and then minus 1. End parentheses in the denominator, and we should be good, right? Okay, let's go to our table feature. We talked about that. Oh, I can enter afterwards. Go to our table. Oh, look at that. I got the good numbers in there still, around 0. Okay. Plug in your numbers from your table that you created. Let's see what's happening. Okay. On the left-hand side, as we approach 0 from the left, it looks like we have a clear tendency the function. We got 1.94, 1.99, 1.9995, right? What number are we approaching as we're getting incredibly close to 0? Yeah, it's 2, right? Pretty obvious, right? Okay. Again, fill in your table. All right, what happens if we approach 0 from the right? We go from 2.04, 8, 2.005, 2.0005. Obviously, looks like we're approaching 2 also, right? Okay. Is there a clear tendency? Is there a clear intended height for this function around 0? All right, let's see if we can write now. Ready? All right, it works. Equals 2. That side, as we approach 0 from that side, equals 2, right? Therefore, in general, the limit as x goes to 0 of that function x over square root x plus 1 minus 1 equals 2. Now, if we had to justify this, if they said, why is this limit 2? And it says like justify or explain or something, all we have to say is because the limit as x approaches 0 from the left of x over, it's going to be a lot of writing, guys, so get used to it, equals the limit as x goes to 0 from the right of, I'm going to run out of room, aren't I? I'll squeeze it in. X plus 1 minus 1. And then I like to put equals 2 also. Okay, that would be our justification. Mr. Bond, you're going B slash C because. Do I have to write out because? No, you're fine. Yes.
Could you write just like the limits in the same number?
Nope. Do this. Yes, do this. Yep. This is extremely more specific. These are the limits. This is the value they're approaching, right? Because sometimes we loosely say it in class. Like we want you to write this way for justification. And it's quicker, honestly. All right. Any questions on this problem? Yeah.
We don't have to write out because, right?
You do not. Pretty much everything I write in class, you guys can use for everything, even the AP test. Yep. All right, let's try this piecewise function. Now, I don't know if we need a calculator for this piecewise function. Okay. The limit is approaching 2, or x is approaching 2 for this limit. Let's draw a table. How will this table look? This pen is a little glitchy right now. All right, number to the left of 2, 1.9, 1.99. Mr. Bonley, why aren't you starting with like 1? Because I know we need to approach 2 and get closer to 2, I'm just going to get there right now and not waste a whole bunch of values. 1.999, okay. To the right, 2.1, 2.01, 2.001, that works for me. All right. If we look at this piecewise function, piecewise functions are broken up by the domain. If the domain is this, use this. If the domain is this, use this, right? Okay, for every value that's not 2, the output is 1. For every value that is 2, the output is 0. So what is f of x when x is 1.9? 1. What is f of x, or what is f of 1.99? 1. What is f of 1.9999? 1. Okay. What is f of 2.001? How about this one? Still 1, right? How about this one? Still 1. Because it's not 2, right? Graphically, how would this look? Oh, by the way, is there a tendency for the numbers as you approach 2 from the left? What's the tendency? Is it too easy? Looks like 1, doesn't it? How about from the right? What's the tendency? 1. Okay, let's look at this graphically. Okay, here we are at 2. And then we have this height of 1. For every value that's not 2, the height is 1. That pretty much looks like the limit is 1, right? Around 2. And then if for every value that is 2, we have a height of 0. Does that matter for the limit? No. The limit's the intended height, not the actual height. Sometimes they are one and the same. Remember, it's the intended height. If you're driving along a car, a little pothole in the road, drive fast enough, you'll go over it, right? Okay, so what is this limit? The limit as x approaches 2 of f of x. Still 1, right? Questions on this one? Why don't we use our calculator for this to type it in? This is pretty easy, isn't it? You don't need a calculator for this. All right. Let's look at 15. Again, we're just making a table. evaluating these limits numerically. Around 0 is kind of nice. It's probably still in our calculator, right? Negative 0.1, negative 0.01, negative 0.001, 0.001, 0.01, and then 0.1. Where is the absolute value key at? So we have to type this in our calculator now. I go in here and clear out my y1 function. I have no idea where the absolute value key is. Math, and then arrow over to number, and then ABS, absolute value, you bet. Hit enter, and there it is. It looks like an absolute value, right? Okay. We need x inside the absolute value, arrow over to get out of the absolute value, then divide by x. Now, before we get crazy evaluating this, like I say, sometimes these functions are pretty easy. We don't need a calculator. Okay, let's think about this for a second. Over here, for every one, I'm going to have absolute value, negative 0.1, all over, negative 0.1. That becomes positive 0.1, right? Over a negative 0.1. What's that equal to? Negative 1, right? You're taking the absolute value x divided by x. Okay. For this value, negative 0.01, what's the output? Still being the same, right? How about this one? Okay, and we can clearly see in our calculator, if we go over to table, we can clearly see we got the answer right, right? Okay, now when we input a positive value, if we input a positive value, do we really need these absolute values? No. If we have only positive numbers, we really don't need the absolute value. It's just going to be x over x, which is 1. So this is always 1. Okay, let's do a little bit more writing. What is the limit as x goes to 0 from the left of absolute value x over x? What can we conclude from our table that we created? What's the intended height as we approach 0 from the left? Negative 1. What is the limit as x approaches 0 from the right? Positive 1. I think we can clearly see that from our table, right? We've shown a tendency. We've shown a pattern. Therefore, what is the limit as x goes to 0 of absolute value x over x? I would not say undefined. What would I say? I would say does not exist, because limits don't exist. Functions are undefined, right? So the limit does not exist. Ooh, now here's the kicker. Why? Because what? Huh?
The intended heights are provided directions.
Okay, let's be a little more specific.
They don't equal each other.
What don't equal each other?
Intended heights of both functions.
Be more specific. When I say be more specific, I mean I want you to use better notation and be specific about the problem we're talking about. Yeah?
The limit as x approaches from the left is not equal to the limit.
Be a little bit more specific. The limit as x approaches what?
0.
From the left of x over x, absolute value x over x does not equal the limit as x approaches 0 from the right, absolute value x over x. Okay? 100%, you can write this out. Show your work, write this out. If I say explain yourself, or justify, or state a reason why. Okay, we had, what was it, 2 of them that had limits. We had this one does not have a limit, right? Limit does not exist at this value. Take a second and figure out what this one is. Okay, we're going to 0 again, which is kind of nice, not to change our numbers. And pop quiz, what mode should our calculator be in all the time when we're in calculus?
Degree? Radian.
Radian. So yes, make sure your calculator is in calculus mode, not physics mode. See what you get. Type that in your calculator, see if you can come up with the left-hand limit, the right-hand limit as x approaches 0. See what happens. Okay, negative 0.1, we get 0.544. Negative 0.01, I get 0.506. So I'm thinking, looks like we're going to 0.5000, right? That's what my first instinct is telling me. But then I look at negative 0.001 and like, what is going on here? It's not 0.5006 or 5.500 something. It's negative 0.8269. That does not show a tendency, does it? Well, I'm going to try something because I think the numbers are just lying to me. Let's go negative 0.000001. Let's add some more zeros. See what happens. That was unexpected. Well, what the heck? Now we go over here. We got negative 0.54, negative 0.50, and then 0.82. Can we see a tendency? I don't think so, right? I don't think we can say something about this. I even changed some numbers and it looks weird. Well, let's go to the graph and see what happens. There you go. There's a graph at a 10-10 window. Can't really see what's going on. So you can either adjust your window size or zoom in. I'll show you both ways to do this. Zooming in, you just go zoom in. And then that's the center of zoom. Well, I added a couple little zigzags there. Well, it kind of seems like the limit is 0, right? But we better zoom in some more. Let's zoom in again. Well, that's some more zigzags. I don't know if it's still 0 anymore. Well, let's go to window. I want to change the window. Let's go negative 0.1. Let's see what happens. And then 0.1. So we have a width of 1/10. Let's change the height though. I want to be able to see the top end. So let's go negative 2. I think negative 2 might work. If it doesn't, we'll adjust. Let's go positive 2. Obviously, you guys should be able to move faster than I can because it's a little cumbersome with the computer. Calculator should get very quick at this. Graph. And that's a lot more zigzags than I thought was going to appear. So that was a width of 1/10. The more we zoom in, the more it zigzags, right? Well, I haven't done this yet. Let's change the window even more. Let's go 0.01. Let's see what happens. Minimum would be negative 0.01 actually. Negative 0.01. I hope it zigzags a whole bunch. Does it zigzag more or less? More? So oh, jeez. So the more you zoom in, the more it zigzags, right? Go down to Ant-Man size and it's going to zigzag even more. Well, let's see. 0.001. I don't think I've ever done that before. Sometimes it's good to be genuinely curious about academic stuff. 0.001, just to see what happens. 0.001. Sure hope it zigzags more. Oh yeah. What are we at? Are we at 100th? 1,000th? Jeez. So what do you guys think? Is there a limit? Does it seem like the graph is settling down on a number on the center of this oscillation? Right here at 0. 0 is the center of oscillation. Does it seem like that graph is settling down? I don't think so. I think the more we zoom in, the more it oscillates, right? So, what's our answer for this problem then? What is the limit? Is there an intended height? What do you got?
Isn't it 0?
The more we zoomed in, the more it oscillated. The closer and closer and closer we got to 0, we made the window smaller, the more it oscillated. Does it seem like there's an intended height? What do we say when there's no intended height then? Does not exist, yeah. DNE does not exist. And we say that because 0 is the center of oscillation, the limit does not exist. It just keeps bouncing between two values, right? It doesn't settle down. Now, out on the outside edge, maybe on that oscillation, we could have a limit somewhere away from 0 a little bit, but right in the center of oscillation, we cannot say that there is a limit. Okay, and clearly you guys have your table, your table filled out. That did not show a tendency, right? So that's how it would look on a table. That's how it would look on a graph. All right, so we come to the last thing for today. 3 reasons why limits fail to exist. We now know all 3 of them. Number 1, f of x approaches a different number from the left side as it does from the right side of C. And how would that look? Pretty easy. We've seen it a couple times already. So number 1, graphically, we would have something where, okay, if this was C, you'd have something like this, right? If this was C, you'd have something like this, right? The limit as x approaches C from the left of our function does not equal the limit as x approaches C from the right of our function. Okay. If this was f of x, the limit does not exist at C because the limit from the left of C does not equal the limit as x approaches C from the right. Number 2 is one we looked at yesterday also. F of x increases and or decreases without bound as x approaches C. How would that look? If we have C right here, we have some function and then it shoots off towards infinity like an asymptote or something, right? Now, we talked about the limit doesn't exist at C, but the left-hand limit as we approach C would have a tendency, I mean, it goes to infinity, a descriptor, not a tendency, I shouldn't use that word. The intention is to go to infinity. The limit does not exist in general, but we can say the one-sided limit goes to infinity, okay? And then number 3, the one we just learned, let's put C right here. We're cruising along on our function. All of a sudden, chaos, and then we're back again. C's got to be, that doesn't look like the middle, does it? I'll go like this a couple more times. There, that looks more like the middle. I just add a whole bunch in here. That value C in the center of this oscillation garbage, that would be the point at which the C value, at which the X value, at which the limit would not exist. And what's the reason? Because f of x oscillates between 2 values at C. Yeah.
So like as like you zoom in closer and closer to that C value, it continue to like
Yeah.
yeah.
Just like it did in that previous graph, it just keeps going and going and going. Later on, we'll learn another way why a limit would not exist, but it's at when x goes to infinity. It's a different type of oscillation.